It was therefore thought that the structure of benzene may involve a closed chain or ring carbon atoms. Consequently, a number of such structures were proposed by Dewar, Calculus, Armstrong, Thiele, and Kekule, but the only structure which could account for nearly all observed properties of benzene was the hexagonal formula proposed by Kekule. It showed all the hydrogen atom to be equivalent and therefore justify the formation of one and only monosubstituted benzene. Moreover, it could also explain the addition of three molecules of hydrogen or halogen to benzene. But Lindbergh objected to Kekule's formula on the ground that it should yield for this disubstituted derivative one meta, one para, and ortho. It may be noted that the two ortho structures shown above differ in the position of the substituents relative to the double bond. Kekule overcame this difficulty by suggesting that the double bond in benzene were not static but in a state of rapid oscillation between two form 1 and 2 as shown in figure. Due to the oscillation of the double bond, there was a state of dynamic equilibrium between the two forms. As a result, the two ortho disubstituted derivative could not be distinguished or separated from one another. Fifth, limitation of Kekule structure. Even though Kekule could justify isomers number of various substituent benzene by postulating the concept of oscillating double bond, yet his formula had certain serious limitations discussed below. Unusual stability of benzene. Kekule structure involve the presence of three double bond in the benzene ring. As such, benzene should be a highly reactive compound capable of undergoing addition reaction very readily. But in actual practice, benzene is found to be unusually stable and not very reactive as shown by the following facts. Chemical reaction. As already stated, benzene rarely undergoes substitutions reaction in the which the typical ring system is retained but is resists the formation of addition product and is not the affected by oxidizing agent such as a potassium permanganate. This only means that benzene ring is very stable. Heat of hydrogenation and combustion. The observed value of heat of hydrogenation is 151 kilojoule mole per minus 1, lesser than the theoretical calculated on the basis of Kekule structure. This means that benzene has a lower energy content and is more stable than the Kekule structure by about 151 kilojoule mole power minus 1. Similarly, heat of combustion of benzene is nearly 150 kilojoule mole power minus 1, lesser than that accepted from Kekule structure. Carbon-carbon bond length in benzene. According to Kekule structures, the carbon atom joined to each other by double bond should have a bond length of 134 pm, while the carbon atom linked to each other by single bond should have a bond length of 154 pm. But the X-ray diffraction studies show that all the carbon-carbon bond in benzene are of exactly the same length, which is in the between that of single and double bonds. Resonance structure. The limitation of Kekule structures and the failure to assign any other satisfactory valence bond structure to benzene ultimately lead to the use of concept of resonance to solve this problem. According to resonance concept, benzene is a resonance hybrid of the structure 1 and 2 as shown below. This implies that the true structure of benzene is represented neither by 1 or neither by 2. It lies somewhere in between the two, as the contributing structures are exactly equivalent and of the same stability. They contribute equally to the resonance hybrid. The resonance hybrid has 151 kilojoule per mole of energy, less than either of the contributing structure as determined by the heat of hydrogenation or heat of combustion value. This represented the resonance energy of the molecule. It is evident that in the resonance hybrid, the bond which linked the carbon atom neither corresponding to single nor double bond On the other hand, all the bonds are equivalent and are intermediate between single and double bond. It may be pointed out that Dever had also suggested some contributing structure of benzene as shown below, but these structures are not given much importance because it is not possible to have formula bond between para carbon atom. Evidence in favor of resonance structure. The resonance structure hybrid is supported by the following evidence. Carbon carbon double bond. According to the resonance hybrid structure, all the carbon carbon bonds in benzene are equivalent and are intermediate between single and double bond. This is in keeping with the observation that all the carbon carbon bonds in benzene are of the same length, which is in between that of single and double bond isomer number. Since all the carbon carbon bonds and benzene are equivalent, there can be no distinction between any two ortho disubstitution product, and there are three disubstitution product in all. Unusual stability and remarkable behavior. The unusual stability and remarkable behavior of benzene is easily understood in terms of its resonance energy of 151 kilojoule per mole, as shown by heat of combustion and hydrogen. Molecular orbital picture. According to the molecular orbital concept, all the carbon atoms of benzene are in a state of sp2 hybridization. The three hybridized orbitals of each carbon are involved in the formation of three pi bond, two with adjacent carbon atom and one with hydrogen. Thus, all the six carbon and the six hydrogen atom lie in the same plane, and each of the bond length is 120 degree. As far as the unhybridized p orbital of each carbon atom is considered, it can overlap to small but equal extent the unhybridized p orbital of both the adjacent carbon atom. Thus, the odd electron in the unhybridized orbital of each of the six carbon atom can form pi electron cloud involving more than two atoms. In other words, the pi electrons are spread over or extensively delocalized, and this results in the formation of a molecular orbital embracing all the six carbon atoms. The net result of this delocalization is that there are two continuous rings like electron clouds, one lying above and the other below the plane of atoms, as shown in figure. The bond angle and bond length in the molecule are depicted in figure. Evidence in the favor of orbital structure. The molecular formal orbital structure enables us to imagine a structure of benzene which corresponds to the resonance hybrid of the calculus structure. If offers as a satisfactory interpretations of the unknown characteristics, physical as well as chemical, of benzene as discussed below. Flat ring structure. The hexagonal ring in the benzene molecule is found to be uniplanar or flat, and each of the bond angle is 120 degree. This can be easily justified in terms of sp2 hybridized state of carbon atom constituting the ring, number of mono and di substitute product. According to molecular orbital concept, all the six carbon atom in the molecule are completely equivalent to one another. Similar, all the six hydrogen atom also occupy equivalent position. Therefore, benzene should form only one more